All right, folks, this is a solution to the projectiles problem number 7. This is the symbolic one. The first part of this video is just a kind of explanation of the problem, so you can kind of skip ahead until I start writing things if you want to just get to the solution. We have an adventurer who's trying to get across a river. The river is a certain width from the point where the adventurer leaps until where they land. And there's a height difference between where they're leaving the ground and where they land. And that's important because this initial velocity, when they run off the edge, they're running horizontally off the edge. So this isn't someone who's like jumping like a normal person would do. They're like literally like running off the edge of this part and it's falling to this edge. And they need a certain speed to make it across. If they exceed that speed, then they're going to land like further away from the edge of the river. If they come in at less than that speed, they're going to land in the water. And so this problem is asking for what is the like magical speed that you could have to land exactly at the other edge of the river. And so that's the problem that we're solving. I set up my axes so that the person leaves the ledge at the y-axis and they land on the riverbed on the other side on the x-axis. Sorry, that should say x. So the origin is actually a point that the person never touches, but the general rule is you want the leftmost point on your picture to be the y-axis. So that's going to be where the person jumps. And you want the lowest point on the picture to be the lowest point that the object gets to. So they're going to get to the ground over here. That's lower than the first part of the river. So I made the x-axis along here. So now I'm going to start to fill in some values. So x naught is going to be 0. X is going to be W. And so that's important because they're going to have to get to exactly that edge of the river because I want the minimum speed possible to get there. Any speed above that is going to get greater than a distance W. The other important part is Vx naught is going to be V naught according to the symbols in this equation. The key word in the problem is horizontally. And so that means that the entire speed that they're using is horizontal. That also means that the initial y velocity is going to be 0 meters per second. So those are like some critical things for you to read from the problem. The other values that you can put in, y naught is going to be h, and y is going to be 0 meters. So the person is essentially jumping from a height of h to a height of 0, according to my diagram. The only other part of this is acceleration, and you're going to want to put in negative g. So the value of g is 9.81 meters per second squared, and so when we use it as an acceleration, we use it as negative g. And so we have this task that we have to come up with an expression for this initial velocity in terms of W, H, and probably little g. And so we're going to pretend that V naught is kind of the ultimate unknown, and we're going to just see how we get here. So there's a couple different ways you can approach this, but I'm going to start in the x direction because our final variable is going to be in the x direction. So the only equation that describes horizontal motion for kinematics is this one, and I can pretty quickly fill this in as W equals V naught times time. And so I'm going to just rearrange that. If I divide both sides by time, I get V naught equals W divided by time. And so I'm going to save this because this is an expression for V naught. It's in terms of W. It is not yet in terms of H and little g. And so I'm going to have to substitute something in for T. And so I can do that with the Y direction. So I can like save this for now. And I kind of have my goal. I know that I need to get rid of that T. If I use the Y direction, I can substitute T equals something into this expression. So for the Y direction, I notice that I'm not involving Vy. So I'm tempted to use this equation just because this is the equation where Vy is missing. So I don't even need to involve that at all. Let's see, so about this equation, the Vy naught term cancels, and y is 0. So I can fill in 0 equals h plus 1/2. Now acceleration in the y is negative g times t squared. So I can simplify this, and I can subtract 1/2 negative gt squared from both sides, and I end up getting 1/2 gt squared equals h. And so to do some algebra faster than you might want to write it, I'm going to multiply by 2 and divide by g. I get t squared equals 2h over g, which means that t is equal to the square root of 2h over g. And so what I have now, I have my expression for v naught. It's in terms of w, but it's also in terms of t. And I have an expression for t. The expression for t is in terms of h and little g, and that's good because what I can do is I can substitute that expression for t into this expression. And what I get is v naught equals w over square root of 2h over g. Now, this is an acceptable answer. This is an expression for v naught in terms of w, h, and g. You are probably trained to try and get that radical out of the denominator or do some other simplification, but you don't have to. The one thing you can do is understand that this fraction, like v naught, can be written as w times the inverse of 2h over g. The inverse of a fraction is just flipping the fraction on top of itself. So the probably like cleanest way to write this answer would be v naught equals w times the square root of g over 2h. And so either this expression or this expression would be probably the best answers to this question. You want to try and avoid doing a lot of algebra once you satisfy the problem, because the more algebra you do, the more likely it is for you to make a mistake. So there is your solution to question number 7 and the symbolic question. Thanks.